Alright, here's what I think is sort of a tricky derivative problem. And I say it's tricky because you have to apply theorem 2-9 and you need to be you need to be good at like interpreting that theorem. But anyways, so we have all this stuff. So we start with the hint. So let G of t be f of tx, which by homogeneity is t to the m times f of x. Now we're going to compute the derivative of g in two different ways, and they have to be, and set them and evaluate them at t equals 1. So the first way is going to be through just standard calculus. What is happening? There we go. No. Okay. Then G prime of t is, well, we take the derivative and f of x is just a constant, so we bring down the m, t to the m minus 1, f of x. So g prime of 1 equals m times f of x. And we look at the right hand side and that's exactly what we have. So yeah, this is looking promising. Okay, so to compute g prime of t, I have no idea what is happening up there. Using theorem 2-9, we want to write, so g of t, which is f of tx, we want to write this as capital F of t. And I'm going to use tildes whenever I'm referring to things that came from the statement of theorem 2-9. Because theorem 2-9, of course, involves functions which are referred to like as f and g, and in particular gi's. But in this problem statement, we have f's and g's. So we can't really, it would be really confusing if we use the same notation. So I'm going to use tildes whenever I'm using function names and variable names that come from the statement of theorem 2-9. Okay, so typically in theorem 2-9 you have capital F of t, or capital F of whatever, and here I'm going to call it capital F of tilde. I want this to be F tilde of, oh my god, please don't be like this, G1 tilde of t all the way through G, and then it goes up to GM. But we're already using M, so go and call that M tilde of t. So in order to make these things look like each other, we need to, thus we set F tilde. F tilde is going to be precisely F, so that part's not too confusing. And for each I, gi of t is going to be, well, we want the input of f to be t times x. So we want the ith coordinate to be t times xi. So we want g tilde I of t to be precisely t times xi. And this is going to hold for, well, x has n entries because the domain of f without a tilde is n, is Rn. So this is going to be for I equals 1 through n. And of course, that's the maximum number of tilde g's, and so n must be precisely m tilde. Okay, so then we have, so we can actually compute it now. Compute d1 f of t. No, capital F of t. Capital F tilde of t. Okay, Now, an important thing to keep in mind here is that f tilde is a function of t. So when we say d1, this is the derivative with respect to the one and only variable, which is t. Which is not to be confused with, like, the first coordinate of Rn. This is the derivative with respect to t. So this is, just by using the theorem, the sum from j equals 1 to m tilde. And we take dj of f tilde of tx. And of course here, dj, now these dj's are actually referring to the coordinates in Rn, because the domain of f is Rn. And then we multiply by d1 of g tilde j t. And here, of course, d1 now, this is back to being the derivative with respect to t. This whole keeping track of like what these di's and dj's refers to, this is tricky. Or at least in my opinion, it's the trickiest part. Okay, so now let's start rewriting these. So instead of j, we're going to use I so that it matches with what we have in the problem statement. And m tilde is n. And then f is the same as f tilde, so we just have di f of tx times, and now d1 gj g tilde j of t, this is going to be the derivative with respect to t of t times xi. And so then this is just sum from I equals 1 to n di f tx times, we'll take the derivative of t, you get 1, so we just have xi. So if we evaluate this at t equals 1, we have d1 f tilde of 1. Well, this is d1f, since f tilde of t is equal to f of tx, this is d1f at x. And so then this is wait. Yeah, sure. So then this is the sum from I equals 1 to n. Now we just have xi times dif, and now we just have x on the inside. Hence, if we look at this, we have the sum from I equals 1 to n of xi dif of x. Well, this is the derivative with respect to t of, here, let's write it like this. This is going to be the derivative with respect to t of f of tx evaluated at t equals 1. And so then this is, of course, the same as g prime of 1, just by definition. And that's m times f of x. And that's what we wanted to prove. So basically, this boils down to another classic example of, in math, where if you want to prove the two things are equal, you take one thing and you compute it in one way, and then you compute it in the other way, and then the two ways that you computed this thing, those two things that you end up with must be the same thing. And so we took the function f of tx, and we computed the derivative of f of tx with respect to t, and evaluated it at 1. And we did this in two different ways, and got two different formulas. And so those formulas must be the same, and that ends up being this formula that we were looking for. And so, yeah, again, I think the trickiest part of this exercise is knowing exactly how we're applying Theorem 2-9, because the Theorem 2-9, there's a lot of moving pieces, and you need to keep track of which of those moving pieces are you using in this particular exercise. And, like, yeah, the different functions and variables in Theorem 2-9, what are the corresponding functions and variables in this particular problem? And of course, like I think one of the more difficult parts is the fact that you're taking the derivative, like d1f, you're taking the derivative with respect to t, but or d1 capital F tilde, you're taking derivative with respect to t, but di f tilde of tx, you're taking the derivative with respect to the spatial coordinates. So yeah, once you have all of that sort of worked out, and you can do it. I use these tildes because that sort of helped me keep track of what comes from this problem statement and what comes from Theorem 2-9. You don't have to do it that way. There's probably much more elegant ways of doing it, but at least for me, this made the most sense to me, and it was how I was able to make this make sense to me. But yeah, that finishes this exercise, and so we're done.